Hello, and welcome back to the course on Big Data as part of this BSc degree in data science from IIT Madras. We're into week six as of this week, and in this set of lectures, we'll actually be taking a deep dive into SQL and specifically SQL for big data. So far, we've had a chance to look at the different types of ETL patterns. Maybe you have also already implemented some of them as part of your week assignments using PySpark. That would have given you a very good sense of the power of PySpark using this procedural programming and functional programming interfaces. With SQL, we start to open up a different interface altogether into big data because, first and foremost, SQL is completely different in terms of how it handles data, how you express different types of functionalities on top of it. But second and more importantly, the way that SQL in turn um, looks at optimization and looks at how to work at very large scale is actually quite different, quite significantly different from how Python works. So it is important that you understand the differences. In practice, you might actually find yourself using a mix of both. Um, like for instance, one of the common patterns that I myself use is SQL for all kinds of common functions and data transformations that I want to do. But the moment I want to do something a little more complex and SQL does not have any ready-made functions for it, it's easy for me to think about using PySpark for it, and that's how you can interleave operations between the two interfaces. Spark as a vehicle is actually very good in that respect because it doesn't have an opinion that you should use just one, right? You could actually have a bunch of these interfaces be used together and still operate within the context of the Spark environment. So the infrastructure that Spark provides is decoupled from the choice of the interface that you might have at the front end. So that's pretty powerful. That's pretty, uh, pretty cool, I would say. And one of the reasons why it's so popular amongst data scientists, data analysts, data engineers. Okay, my name is Rangarajan Vasudevan. So we're on to week six now. Let's start. SQL stands for Structured Query Language. I believe some of you have had to go through a specific course on SQL earlier. I'm not going to, spend too much time on the foundations of SQL or the specifics of SQL that are going to be pretty, pretty straightforward to understand if you've done one of those courses, or they might have already been done to death. I'll instead focus on some of the critical, concepts which I can just summarize over the next like maybe 20-30 minutes. And once that's done, we'll start to take a look at how SQL in the world of big data works. What are the things to keep in mind, etc., etc., as a data engineer? As you might already know, some of you might already know, SQL stands for Structured Query Language. It's an acronym. When it started out, it wasn't an acronym, actually. The history of SQL is that it started as a sequel meaning a follow-on event, which is supposed to be better than the predecessor. And the predecessor was some other system called a stair, I think, again built by IBM, some researchers at IBM. But that earlier system was quite kludgy. There was a lot of work that was required for it to be used. So they thought, okay, there needs to be some simpler ways of dealing with data. And coincidentally, around the same time, there was this landmark paper that was published by this researcher called Edward Cobb, who looked at data from a relationship perspective. Instead of just looking at data as just a bunch of random objects being stored in a file, he was the first to postulate and expound on like a mathematical definition of data using relations. So when we conventionally refer to databases as our relational database management systems, the word relational actually has a mathematical connotation, the same mathematical connotation that the word mathematical functions have, right? So a relation takes mapping from um, a domain to a range, right? That relation, that mathematical notion, is exactly how Cobb looked at the world of data. The paper was published in 1970, seminal paper, one of the first to actually talk about how relational models of data are more conducive for a variety of different types of functionalities that you want to express on top of it, and that became extremely foundational as a thought process. So when these researchers at IBM, they were looking at the next version of that data processing tool, they decided to model it on the Cobb paper, um, and from then followed multiple other inspirations. For instance, one of the earliest systems was called as rather one of the earliest companies that took on this in a big way was itself actually called as a relational system. The company was called Relational Systems. Later on, which changed its name to Oracle, and that's how we know it today, Oracle database. But when it started out, it got so inspired by Cobb's paper, and it also thought that it could do a much better job than IBM did in terms of implementing the thesis of how data needs to be looked at as relations of objects with relations of elements with each other. So it was one of the first systems to out and out design everything around data processing as a relations using relational algebra. So Cobb's paper was the first to talk about the mathematical foundations of a database. Actually, not a database, a data processing system, um, and he called it relational algebra. Just like you have other forms of algebra, other branches of algebra like linear algebra and so on, right? Um, so a relational algebra meaning a way for you to fundamentally think about relationships between data and express operations on top, so that you don't have to worry about lower level abstractions, right? So math is really good at this, building these abstractions on top of abstractions. So that's how he constructed it. So we will take a look at SQL from that standpoint, because SQL, when this IBM's folks implemented it, they looked at it as an implementation of the relational algebra concepts that Cobb had come up with, and those relational algebra concepts have really stuck to this day in terms of how the SQL language itself has evolved. What are the different syntactical flavors it provides? How does it plan? How does it execute? How does it optimize? All of that. Okay, so keeping true to the spirit of working at a level of abstraction, SQL was one of the first programming languages to formally implement a declarative style of programming. What that meant was, you declare as a programmer what you want to do, but you don't declare or you don't specify how you want to do it. So that's a big difference compared to, let's say, procedural programming. So let's say, for instance, you have to work with some data in Java or Python. You would not only have to define the model of the data, let's say in the form of a class or in the form of an object or a structure, but you also need to then think about how do I make those operations happen. So, for instance, if I need to be able to edit a particular object or create a record or create a data element which looks like that object, you have to formally create an instance in Java of that object. That in turn allocates memory on the heap, and then you have to go populate the different elements in that instance. And then once you're done, meaning you write into a database or write into a file, then the destructor gets called and it frees up the memory. For more complex things, you have to, like for instance, you have an array of values and you want to do something about it. You have to formally declare what is the nature of the storage where you're going to keep this array of values. It could be one of the Java collections, but you have to explicitly specify it, right? Otherwise, the program will not compile. Um, like for instance, a linked list or array linked list of whatever it is. Then you also have to worry about in other kinds of languages like C. you have to worry about the memory management itself. At least Java has some automation built in around it. You don't have to, actually manage the objects yourself as a programmer. But in a language like C or C++, you have to manage that as well. And not only are you saying how to go about doing an operation, you're also explicitly saying that I want the operation to have this kind of an impact on resources, and therefore I want to manage those resources myself, right? So that's getting down pretty deep in terms of the level to which you have to think about programming. Um, so those are all examples of procedural programming. Functional programming is a completely different school of thought. So there, it's about how do you chain logically occurring operations together in such a way that you deal with the output of one being the input of the other, and logically look at every single step as producing outputs for somebody else to consume. So that allows you to chain a bunch of these commands together, and it makes for easy reading. But even there, there's a lot of work that goes on behind the scenes in terms of things like resource management and specification of how certain operations get executed. So even that is not declarative, right? It's functional certainly, because you deal with functions as the fundamental unit of operation, but I mean not objects, not classes, but functions. But then again, you have to also think about the how and explicitly program the how as well. Whereas with declarative, the focus here is don't worry about the how, focus on the what. The what needs to be done. So if you need data to be processed in a certain way, like let's take the same example. If you need data to be created in a certain way, um, you can just simply use a specific SQL syntax called as insert into table values, and you create data of a certain type. You don't have to worry about creating an instance in memory, populating that with data once it's written to the table or the file, then going and cleaning up the memory instance. All of that is just automatically done for you. The other angle to declarative is the fact that you don't have to actually worry about non-functional requirements. What that means is whether the data operation happens with this much speed or with much better speed, whether it happens on a system which is tolerant to failures or not, whether it caters to multiple other concurrent users coming and trying to query the same table and get some answers. None of that actually should matter to you in terms of a programmer, and that's exactly also what declarative means. So you don't have to worry about any of that, and the system just takes care of it automatically. So the how of performance, the how of availability, fault tolerance, all of that is actually also handled by the implementation of the SQL system. Now, in practice, you would find that there are multiple different types of databases which implement SQL, but they've all left the non-SQL pieces, right? Meaning the how parts or the non-functional sides, right? To varying degrees of maturity, and that depends really on how much of a mature database, how much of a database of certain type of functionalities do you need, right? You pretty much can start with something which is super lightweight, which you just embed as part of your Java application, as an example, and not have to worry about shipping extra code or extra complexity. You can start like that, in which case there is no availability, there's no fault tolerance. It's just an in-memory database which dies the moment that machine reboots, as an example. Like the example here is Berkeley DB. But then all the way on the other end of the spectrum, you have like something like Oracle or Postgres or MySQL, extremely mission critical systems which are configurable to do all of those things I talked about and support the SQL language that is prescribed by the standards, with the ANSI standards. So all those options are available. One of the first things that that is implied by the way that SQL was designed is that because it fundamentally helps you model a relation, which is a mathematical function which takes um, values in a domain and takes it to a range. Naturally, it's not going to be limited to single values alone, right? In fact, more generally, the entire domain of values, which is possible for the uh, on the input side, right? All of that is fair game, meaning all of that can be legitimately provided to the relation, and it's supposed to actually have a output associated with it, like basically the range of values associated with it. Therefore, the way to think about what SQL operates in as a fundamental unit of operation is a set of records. Now, a set can mean as little as just one record. It can mean as big as like a million, billion, whatever, right? But it's a set operation. That's what it's geared towards in terms of specifications. So keep that in mind. Unofficially, you could say that SQL is actually one of the most popular language for data analysis. I'm saying unofficially because this is one of those religious debates which you could, fight on one side and still be right, and nobody's going to actually, make you repent it, right? SQL has been so popular that it probably is the easiest, or rather, I would say, easier language of interface, easier interface to pick up for data analysis than an out-and-out programming interface like Python or R. So you'll find a lot of data analysts getting their starting exposure to data science or analysis in general using SQL because they don't come from a computer science background, as an example. And that could be true for many of you as well. And that's perfectly fine, right? SQL is great at that, and it's very good at helping you get warmed up before you start to need more complexity and need more power. Yeah. Like I said, it's fundamentally modeled on the mathematical notion of a relation. Therefore, obviously, it's very conducive for relationally structured data. In fact, the word relationally structured data obviously comes from RDBMSs, like relational databases, which in turn come from relational algebra. So I'm not trying to, make this like chicken and egg dependency. The arrow is very linear, and it's because SQL was relational algebra. That's how all of these terms originated or derived over a period of time. But what I really mean by conducive for relationally structured data is that SQL was very good at operating on a set of records where the records look the same. That's what I mean by this, right? So the set is basically is defined by multiple rows, row one to row 10, whatever, right? If you think about it as a matrix, those are the rows of the matrix. The columns are basically the field values, which are homogeneous, which means all those records have either at least a null or if not an actual value for each of those elements, right? So that's what I mean by relationally structured data, like data that you can put into a matrix. Tables in RDBMS, of course, is one of the best examples, but also data frames, right, that you see in Python or Spark. All of that is actually also very, very conducive to be operated on using SQL. Yeah, so we spoke about this briefly, that SQL is actually an implementation of the theory of relational algebra. What is relational algebra? Let's just dive a bit deeper into it, and then we'll get into the specifics of how SQL gets used in big data. So, in relational algebra, you are effectively operating on data sets with some common operator types, and those operator types are just few in number. And then you basically have the ability to construct elaborate, complex, chains of workflows, chains of data processing, steps, which all built on top of each other, right? So these operators are foundational, and you could just like you could construct an equation in linear algebra as an example. Here, you would construct an elaborate statement which just in, progressively builds up on the the relation that the previous step has left off with. Um, so in a relational algebra representation of an operation, it's usually in the form of a tree. It's a tree structure because there are no loops. It's not possible for you to link the source table back to the specific operation that happens and have that be cyclical in nature. That does not make sense in relational algebra. It's unidirectional in terms of data flow, and it's a tree structure also because you could have arbitrary levels of nesting, arbitrary levels of branching. So that all of that is possible. So it serves the need for some very complex operations that you might want to perform. So, what are those common operation types in relational algebra? The first is what's called as projection. A projection is conventionally in the world of SQL is called as select. A projection is basically saying I might have multiple data elements, but I'm really interested in only a projection of those data elements um, uh, onto their respective axes. So think of data as being multidimensional, where each dimension is basically each column. Then a projection is basically taking the set of data from your entire corpus and projecting the values of those records that you picked up onto the axis that you're interested in. You're not interested in on the other axis, in this multidimensional axis, multidimensional world of this data. You're only interested in certain axes. So you're projecting the actual values of the records, actual records onto those axes. So when you do that, what you get is the value of that column for all the records, right? Because you're projecting them, and you might pick few columns, and therefore you get only those values, as opposed to the rest of the values. So so the world of projection is actually quite literally like the geometric projections that we see in algebra. The second operator is selection. Selection is basically, like the name suggests, you're selecting certain records based on some conditions. Effectively, these are filter conditions, and those filter conditions can be expressed using filter clauses. In the world of SQL, the keywords typically used associated with it are where and having. Right? Then, just like relations in mathematical terms, you could also have other types of standard set operations. So these are Venn diagrammatic set operations that you've learned about already in junior school math, right? Think about set intersection, set union, set overlap, set difference. All of those things are possible here, are applicable. Yeah. So you treat the data as a set, and then you can just start doing all kinds of things with it. SQL by default, by the way, treats its foundational unit. The default unit is actually a multi-set, not just a set. The mathematical definition of a set is a unique set of values. Multi-set has no such uniqueness constraint. It's just basically a bunch of values, right? The values could be repeating, need not be repeating, doesn't matter. SQL adopts the multi-set definition, strictly speaking, not the set definition. If you need a set from a multi-set, obviously you can just do a distinct. A distinct will give you the unique values. Likewise, in SQL as well, the default table is a multi-set, but then you could do a distinct on top of it and get only the set of values. Okay, set operations apart. The other key operation type that's supported by relational algebra is joins. So here you're referring to the ability to take two relations. They themselves have a certain set of values that they induce on the range, and you can take those and merge them together. If you take those two relations and merge them together, then you're effectively creating a new relation. That new relation has the sum of properties of both these relations together. So, which means it operates on the individual domains that each of these relations operated on. So the merged relation operates on both those domains, and the output it produces is a combination of a juxtaposition of the ranges of both those individual relations. So that's the way to think about it. And we'll see some examples of this later. But yeah, the different types of joins here are key-based joins, equi-joins, outer-joins, etc. And finally, the last set of operations that you might want to think about would be aggregations. So here, um, these are special functions which operate on the set as a whole, and they give you the ability to look at certain, grouped values, like for instance, sum, average. But yeah, obviously, you also have scalar functions, not just aggregations, which look at individual elements of a set and operate on that level, right? And that's also possible. That's also part of the relational algebra notions. So if you look at it as a tree visually, so let's assume, for instance, there are two tables, R and S. So ignore the tabular formulation of it, maybe. We can look at it as two domains, right? Two domains of data sets, R and S. Now, the first operation that I perform is a join. The join is indicated by the hourglass flipped on its flipped 90 degrees, right? So it's a sleeping hourglass position. So in this sleeping hourglass, it denotes the join condition, and then the condition of the join, rather the join operation, and then the condition of the join is specified as a join between these two domains on a specific axis, which is called as in this case B. So in this kind of a join, because the equality condition is used, it's called an equi-join. So once the join is performed, then the output that this relation produces is actually of a certain type, which has all the axes of R, all the axes of S coming together, with only the B axis being common, right? The rest of the axes are just add-ons. And in that multidimensional data set, I'm taking again a specific selection of data which matches the value on a particular projection. So in this case, it's s.c. So against that projection, there is a value of 10. So think about again multidimensional axis. So a lot of different data points clustered in this multidimensional axis. There's an axis called C. In that C axis, there's a value of 10, and for that 10 value, there are a bunch of data points across, right? And I'm picking only those data points which are having this value of C equals 10, and those data points now have extra flavor that come in because of the axis of R, right? Because I've already joined them, and the axis of B is actually common to R and S, but the rest of the axis is unique to R separately and S separately, right? So now I've picked up basically that particular hyperplane of points, which has this particular value of the C axis to be 10, and from this specific set of data that I've filtered, I'm projecting only the value onto column value onto axis A. So the projection symbol is denoted by capital Pi. The selection symbol is denoted as capital sigma. So the R dot A refers to of all these data points which match these conditions from the previous step. I now use this relation to only project onto the A axis, right? All of these points project onto the A axis, and the A axis, let's assume, is just this horizontal axis. So then I get all the values of the records which have matched all these previous conditions prior to the step in the relational algebra tree, and then I pick up only the eighth column from here, A column. So that's how to mathematically look at what SQL actually denotes. All right, so I'll stop with this as the just a quick summary of SQL foundations. We'll now dive deeper into the specific set of that are of interest to us from the world of big data.